Today, we're going to pull back the curtain on a tiny, almost invisible piece of technology that, I'm not exaggerating, is one of the most important inventions ever. It's the unsung hero hiding inside pretty much every piece of tech you own, and it's the little engine that makes our modern world tick.
You know, there's this secret ingredient, this common thread that connects all of those gadgets. It's a microscopic workhorse that takes the faint, delicate signals from the world around us and makes them strong, clear, and actually useful. So, what is it? Well, let's find out.
All right, so before we can properly introduce our hero chip, we've got to understand the fundamental problem it was built to solve. And it all comes down to this: making really, really weak signals useful. Just think about the sound waves hitting a microphone, or maybe the tiny little electrical pulse from a medical sensor. On their own, these signals are incredibly weak. I mean, way too weak to drive a speaker or show up on a screen. They need a boost, and that's where an amplifier comes in. It's basically an electronic signal booster. It takes a tiny input and, using some outside power, turns it into a much, much bigger output. So engineers took this basic idea of an amplifier and just kept refining it until they created something that was basically a perfect, universal building block for all kinds of electronics.
And here it is. Meet the operational amplifier, or as everyone calls it, the op-amp. That little triangle, that's its symbol. You see it everywhere in electronics. At its heart, it's a special kind of amplifier. But what's so cool is that it's designed to behave so perfectly, so predictably, that we can treat it like an ideal tool.
And to make them easy to work with, we imagine these ideal op-amps have 3 theoretical superpowers. Okay, superpower number 1, infinite input resistance. Basically, it can sense a voltage without drawing any electricity at all. Superpower 2, infinite voltage gain. This means it can amplify a signal by a practically unlimited amount. And number 3, zero output resistance, which means it can deliver its new powerful signal without losing any of that strength along the way.
Now I know, infinite gain and all that might sound a little abstract, but here's the thing. It all boils down to 2 beautifully simple rules that engineers use every single day. We call them the golden rules. Rule number 1, the inputs draw no current. Easy enough. And rule number 2, the op-amp will do whatever it has to with its output to make the voltages at its 2 inputs exactly equal. These 2 rules, they're the key to everything.
But wait a minute, a device with infinite gain? That sounds completely out of control, right? How could something that amplifies infinitely possibly be used for anything precise or stable? It seems like a paradox. And that really is the central challenge here. I mean, if the tiniest microscopic difference between the 2 inputs results in an infinitely large output, the chip would just be a switch, constantly slamming back and forth between on and off. So how do you possibly harness that kind of power? The solution, it turns out, is this incredibly elegant and clever trick called negative feedback. It's brilliant. All you do is connect the output of the op-amp back around to its negative or inverting input, and that one connection creates this self-regulating loop that tames the op-amp's wild nature. And this one little wire creates a total transformation. Without it, you've got what's called an open loop. The gain is infinite and totally uncontrollable. But with that wire, you create a closed loop. Suddenly, that infinite gain is brought completely under control, and the circuit becomes this stable, predictable, and unbelievably versatile precision tool. If that sounds a bit confusing, just think about the thermostat in your house. It's the perfect analogy. You set a target temperature, right? The thermostat is constantly measuring the actual room temperature. That's the feedback. It compares the two, and if it sees a difference, it changes its output, turning the furnace on or off to get rid of that difference. An op-amp with negative feedback works in the exact same way, constantly adjusting its output to make its 2 inputs equal. So once we've tamed the op-amp with negative feedback, it becomes this amazing, predictable ingredient, and we can start combining it with other simple components, like resistors, and follow different recipes to build all sorts of incredibly useful circuits. All right, our first recipe is a total classic, the inverting amplifier. Here's what we do. We feed our signal into the negative input through one resistor, and then, and this is the most important part, we connect another resistor from the output all the way back to that same input. See? That's our negative feedback connection right there. And this is where the magic of feedback really shines. The op-amp's own internal infinite gain,
It just completely disappears from the equation. The gain of the entire circuit is now set perfectly by the ratio of those two resistors we added. If you want to amplify a signal by exactly 10 times, you just make one resistor 10 times bigger than the other. It is that simple and that precise. It's incredible.
Okay, let's try another recipe. What if we add more input paths, each with its own resistor, all feeding into that same negative input? Well, this setup is called a summing amplifier. When we apply our two golden rules to this circuit, something amazing happens. The output becomes the inverted sum of all the input voltages. This little chip is now doing math. It's acting like a tiny, super fast analog computer. And that, by the way, is where the operational in its name comes from, its ability to perform mathematical operations. So let's just step back and think about that. This one simple, cheap little chip, governed by two dead simple rules, and this one big idea of negative feedback, becomes one of the most powerful and fundamental building blocks in all of modern technology. And let's not forget the absolutely raw, insane power that we're taming here. A typical off-the-shelf op-amp has an open-loop gain of over 100,000. That's the staggering amplification factor that this elegant trick of negative feedback wrangles into perfectly precise, predictable behavior. So, if you're going to take anything away from this, it's these four things. The op-amp is basically a perfect amplifier. We use two simple golden rules to figure out what it's going to do. The real magic trick is negative feedback, which turns it from a wild beast into a precision tool. And because of all that, it's become the ultimate electronic Lego brick. Which brings us right back to where we started. That powerful, crystal clear sound coming from your headphones? Yep, that's an op-amp. The rock-solid sensor readings in your car's engine or in a hospital's heart rate monitor? You guessed it, op-amps. It really is the invisible workhorse that powers our world. And hey, don't just take my word for it. There is a legendary book in this field, kind of the Bible of electronics, called The Art of Electronics. And the authors put it perfectly. They said, the operational amplifier is arguably the most useful single device in analog electronic circuitry. I mean, it doesn't get much clearer than that. But its true impact was even bigger. The op-amp basically democratized electronic design. It let generations of engineers build amazingly complex systems without having to be experts in the nitty-gritty physics of transistors. They could just grab this perfect building block and start creating. So the next time you pick up any piece of advanced tech, you'll know its secret. Now that you know about the op-amp, what are you going to see differently in the world all around you?